Good evening, ladies and gentlemen. Thank you for joining us at the SAIEE Energy Storage Chapter webinar, where we'll be discussing tonight energy storage technology and need for clean options. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV. The recording will also be made available on the SAIEE website under the Events drop-down menu in the section Past Events and Webinars. This page is updated regularly, so ensure you check back as often as possible for new uploads and subscribe to our YouTube channel. A certificate of attendance will be issued a few days after this webinar. I'd like to now introduce you to our host for tonight. It's Ms. Joanne Dean. She's a board member of the South African Energy Storage Association. Joanne has 18 years of experience in designing and constructing process and flow control plants in the mining sector. In 2000, inspired by Attenborough, Bloomberg, Ban Ki-moon, and her intrinsic need to make a difference to the world, she joined the Chamber of Commerce overseeing government relationships. While busy at the Chamber of Commerce, Joanne furthered her studies in environmental engineering, specializing in waste, water, and energy disciplines, coupled to carbon reduction project development in Illinois and GHG protocol. Armed with practical knowledge, the once wannabe activist evolved into a strategist in developing carbon reduction projects in the waste and energy spaces. She's currently driving 518 REMW project development, mainly in South Africa and the SADC. I hand you now over to our host.
Thank you so much, Minx, for that introduction. Good evening to all, and a welcome from a frosty South Africa, and I'm sure maybe a dark one for many as a result of load shedding. Please note that if you are cut off down due to our friend load shedding, the webinar will be posted on the SAIEE website, or we can encourage everyone to invest in storage to counter this load shedding. Firstly, our grateful thanks to SAIEE for hosting these informative webinars. A bit of interesting information for the non-SAIEE members that are attending. SAIEE was formed in 1909. The South African Institute of Electrical Engineers has grown to the extent that there are approximately 6,000 members on its membership roll. The South African Institute of Electrical Engineers strives to provide leadership to electrical and electronic engineering disciplines to support its members to becoming more effective practitioners. To their quality of life, all communities in South Africa is uplifted. I hail from SAIEE, South African Energy Storage Association, and we are one of the founding members of the SAIEE Energy Storage Chapter, which was established in 2020 to coordinate efforts to build human resources and other capacities in the research and development, commercialization, policy and standard and guideline development, education, training, and popularization of all types of energy storage technologies, such as battery storage, hydrogen generation, storage, thermal, energy storage, mechanical energy storage, supercapacitor energy storage, etc. There are so many. It's such a broad field and such an exciting field. The chapter welcomes all interested individuals attending tonight to become members of this chapter. Come and join us. All you have to do is fill the online membership form. Becoming a member of SAIEE is not essential, but to be a member of the Energy Storage Chapter, however, taking the SAIEE membership is strongly encouraged. 6,000 members can't be wrong. Tonight, we want to unpack on the technologies current in this exciting sector. Globally, energy storage deployment in emerging markets is expected to increase by over 40% every year until 2025. Currently, utility-scale batteries dominate global energy storage, but by 2023, small-scale battery storage is expected to significantly increase, complementing utility-scale applications. Overall, total battery capacity in stationary applications could increase from a current estimate of 11 gigawatts to between 180 to 420 gigawatt hours. That's a 17 to 38-fold increase. This then positions this technology perfectly in the well-known South African's current energy challenges. Tonight, we have Chris Joubert here to tell us more. Chris is a director of African Energy Storage Solutions. Chris served as a senior test engineer with the Datsun Nissan factory in South Africa, and then moved on to Somchem as a senior quality engineer involved in quality planning and testing of explosives and propellants. Chris established Joubert Consult, subsequently taking up African Energy Storage Solutions, AESS, with engineering partners Francois van der Sagie and Wessie van der Westhuizen, following his passion for the renewable energy and the development of the people of Africa, and I'm sure to lead us into this new clean field. Without any more to ado, let's hear from Chris and what he has to tell us tonight.
Good, I'm unmuted now. Good evening, everybody. I would like to speak about energy storage technologies, what's available now, what is probably developing at quite a rate, but in the first place about keeping it clean. And keeping it clean is not just about air pollution, it's about a lot more. It's also about the environment around us. Now, we have a lot of skeptics about renewable energy, as we see in the press, and some people still make a joke about solar power that goes off at night and the wind that doesn't always blow, forgetting about the important role of energy storage. Now, if you look at the forecast some 3 years ago from Bloomberg, they forecasted something like 940 gigawatt hours by 2040. This was updated to about 1,100 gigawatt hours, and it's still climbing. It is going to be one of the huge contributors to going off carbon, and it's quite important to understand the role of this. Also, the Cape Town University, their Energy Research Center, did their alternative IRP report, and this shows actually the big role that's forecasted for storage, specifically with solar and wind, and how that the three together will reduce the coal component by 2050. Now, you see this everywhere. Big storage is the next big thing, and there's also quite a move towards the appreciation for long duration storage. 4 hours is not enough, and this is now expressed by the American government, as well as specifically California, who is doing a lot of work on flow battery technology and specifically long duration batteries. And with long duration, we're talking about 6 to 10, 12 and hours and even months, depending on where you are on this globe. There's a project going now in California to assess the different long duration energy technologies, and one of the technologies that I'm involved with are part of that assessment. So we need to start thinking about long duration for utility scale applications and even mini-grid applications. Now, we see in the press, this is from 2019, but it's continuing up till today, that installations, energy storage installations will grow from 17 gigawatt hour to 2,850 gigawatt hours. That's 2.8 terawatt hours by 2040. There's a further, well, what they predict here, and part of the ongoing story about storage is lithium-ion battery cost per kilowatt hour by 2030 will be halved as demand takes off into different markets. Now, we will see later on that this is actually not going to happen, because there's already a shortage of lithium batteries, and there are other issues around lithium batteries. Total demand for batteries, if we take stationary storage plus the electric vehicle or the transport sectors are going to be around 4.5 watt-hour by 2040. And it's providing, as they say in the press, Bloomberg in this case, a major opportunity for battery makers and miners of component metals such as lithium, cobalt, and nickel. And I think they have missed the boat slightly. This slide gives us an indication of the various roles that storage or in large batteries can play in the different sectors. And I'm not going into the detail. We have a lot of slides, and I'm leaving everything into the presentation so that you can afterwards have a look at more of the detail. Now, there are a lot of different technologies, and this is not complete, but there's like pumped hydro, lithium and other chemical batteries, flow batteries, compressed air, thermal energy storage, supercapacitor, green hydrogen, and then flywheel for very short-term applications, and mechanical gravity, which we will also have a look at a bit later. Pumped hydro has been the biggest contributor in energy storage for a long time. And in South Africa, we have 4 major pumped hydro applications or installations. And the problem is that this has limited potential going further because of our geography. You need to have large dams close to each other so you can pump water up and down as required. Then, looking at lithium and other batteries, there's a new kid on the block, which is Graphene-Aluminium-Ion, which is looking to displace lithium-ion in the near future, but it's not commercialized yet, and we will look at this a bit later. There's nickel-based batteries, metal air, lead acid, sodium sulfur, and then lithium-ion in different states. And we all know about lithium-ion. We can see the green bar there is the contribution of lithium-ion to total battery storage technologies, and it is really the major part at this point in time. At the bottom, you can see that South Africa made a commitment with the World Bank of installing up to 1.4 gigawatt-hour of battery storage in 2 phases. It was supposed to start in 2019, but now it seems like even 2021 is a bit optimistic, but the wheels are turning on this. Looking at lithium-ion, of course, there are many positives. We all know about lithium-ion. We've been using this in our cell phones, mobile phones, and laptops since the 90s. It's got a high energy density. There's a higher cell voltage than some of the other technologies. They've got economies of scale, which is quite important in the market. There's the Tesla hype. I mean, because Tesla is using this and they are really growing at a faster rate, it is a good advertising medium for lithium batteries. It's versatile, and there's intensive research to resolve the issues. But what are the issues? If you look at the negatives, there's the danger of overheating and fire. There's a limited lifetime. During that limited lifetime, there's performance degradation. It uses scarce materials, contains toxic elements like both lithium and cobalt, and it's a pollution hazard. And there are many people that dispute this, but that is what we see all over. Safety issue, we don't have to spend a lot of time on this, but we hear about fires now and then. There's the Arizona fire that was in August 2019, I think, and there's been 28 major fires in South Korea, and it is just because of the nature of the technology. And once it overheats, once one cell overheats, it spreads, and it can cause fire and explosions, etc. And I don't think this is what we want in large-scale utility applications in Africa. This was a recent article, April 2021, of this Tesla vehicle that actually went off the road while it was in auto mode, although they're disputing that now. But it caught fire, and it took them 4 hours to put that fire out. So once it catches fire, it's very difficult to extinguish this. Now, the environmental issues with lithium ion, and it's important for us to really take note of this. In Chile, which is a large producer of lithium, they use huge amounts of water, 1.9 million liters of water per ton of lithium produced. And this is taking away water from a dry country and taking it away from agriculture. In China, they've had huge issues with where they mine the lithium, of problems in the rivers and dead fish, and through toxic chemical leaks from the lithium mine. And this is not what we want, really. And people forget about this as long as they can make a lot of money. And then the other one was the artisanal miners, as young as 7 years old. It was found in the DRC, and this causes chronic lung diseases, etc., from the cobalt dust. They are actually mining this by hand without any safety clothing, etc. Now, if you look at electric vehicles, one Tesla Model S uses 7,104 lithium cells, and that's about 1,000 times as much cobalt as a smartphone, which is 10 kilograms in every Tesla Model S. If we look at utility scale batteries at that ratio, we would need 83 million lithium cells per gigawatt hour of storage, and these things are just scaling to in such a way that we need to take care of what we use in these large batteries. I know there's now eventually, at last, a move away from using cobalt, but still lithium is still in there, and it still shares a lot of the characteristics. I'm not going to stand still at these slides. There are more articles that talk about this. Apple, Google, Microsoft, and Tesla and Dell were sued over child mined cobalt in Africa, and Tesla is now planning to change to lithium iron phosphate cobalt-free batteries in a couple of years' time. And that was forced through class action by DRC citizens. Now, if you look at the electric vehicle sales and the increase that is forecasted over the next 7 or 9 years, this is going to ask for lots of lithium and still cobalt, if all of that will be lithium ion powered. And by 2030, they expect 2 terawatt hours of EV batteries, and other forecasts are on par with that. If you look at storage batteries, installed batteries, then there's an equivalent growth expected, and this is also getting to such proportions that we have to look at clean energy storage for the future. That's also another 2.5 terawatt hour by 2050. There's more things about the emerging field of energy storage and the lithium ion issues, etc. But we need to get to something that's cleaner than that. What they say here is that it cannot be foreseen that lithium batteries will be the technology that will take over mobile and stationary tasks at low cost. And there are more evidence of that. And then, interesting enough, last week, there was an article that's already reporting that lithium-ion batteries are in short supply because of the shortage of lithium. and they're cutting back on EV manufacture and all of that. Demand for electric vehicles and grid renewable storage is rocketing even before solar houses reach the tipping point and need tens of millions more. So in addition, energy independent smart cities need distributed energy storage for their ocean wind and ubiquitous solar power. So, and the references there, you can all have a look at it afterwards. But my plea is that we must prevent Africa from becoming a lithium and cobalt dump. We need clean storage technology going forward. And then people say, but what else? Also in April, just 2 months ago, this press release was made about the Graphene-Aluminium-Ion batteries, and these have a higher energy density, a longer life than lithium batteries, and they're aiming for the EV market and in a big way with this. So they show that it's rechargeable at a battery life up to 3 times that of current leading lithium-ion batteries, higher power density, and they charge up to 70 times faster. Isn't that what we need? And they're not using scarce metals in this at all. The other one is supercapacitors. I've forecasted a couple of years ago that this will actually be powering our electric vehicles in future, and they're getting much closer to that now. The nice thing is they have a cycle life of more than 1 million cycles. I mean, that's a couple of lifetimes of all of us. They can operate in -30 to 85 degrees C without cooling or heating. There's no performance degradation, round-trip efficiency DC to DC of 99%, and it's non-toxic, and there's no risk of thermal runaway. And you can charge them at the current rate with the current technology in the market in South Africa. You can fully charge them in 35 minutes. Now, South Africa actually has the biggest base for supercapacitor batteries in the world at the moment. It's growing fast overseas now, but this was the first country where this supercapacitor batteries were commercialized, and there are many homes, game lodges already powered by supercapacitor batteries. But it's also excellent for electric vehicles, regenerative braking, and trucks, trains, and hoists, etc. So there's a huge application for supercapacitor batteries. In fact, my mouse that I'm using now on my laptop is powered by an AA-sized supercapacitor battery. And people think this is it's a gimmick, but it's really taking place now. The implementation of supercapacitor batteries in China, they use supercapacitors for to drive buses. They charge them at each bus stop for 10 seconds. They're not using large supercapacitors, but this is sufficient to keep them running on their circuit all day. More than 1,000 buses already running on this. Bombardier is using supercapacitors to recover electricity on the braking of trains. 35% of the electricity is recovered in this way. And it's because it can actually absorb a lot of power in a very short time. There's more developments going on. One is the manufacture of vehicle body parts that are actually supercapacitors. And Volvo is working on it, Lamborghini is working on it, and the car's body will be storing energy. So that's still a couple of years off, but it's coming. Kilowatt Labs, they have just announced a 62% increase in energy density for the new generation supercapacitor. These will reach South Africa within the next quarter, I believe. And they also, this is a new prismatic construction of the supercapacitor instead of rolled sheets of graphene, and they can make it in any shape, and they're already doing 80% of the available energy density of a Tesla battery. So the prismatic design also increases the energy density, but in fact also reduces manufacturing cost, and you can fully charge it in 6 minutes flat, which is better than filling your car tank at the petrol pump. Kilowatt Labs is also working on body panels now, and with an energy density of 450 watt-hour per kilogram. So there's a lot of work going on this, and they're already now developing supercapacitors for EVs. And I believe there's I spoke to one of their managers recently, and there's a huge demand from the EV market. There's also a British company, Super Dielectrics. The link is there. You can have a look at their technology. They're not commercialized yet, and I think Kilowatt Labs has the edge on them in terms of commercialization. Then there's flow batteries. They are different. Vanadium redox is the best known in this country because of Bushveld Energy and Bushveld Mining that actually produces vanadium, and they're looking for a market for that. But vanadium is expensive. Zinc bromine is also in the country. And then iron chromium flow batteries, and then the iron flow battery. I'm quite involved in the iron flow battery marketing in South Africa. So I'm not going to give you a marketing pitch, but you need to understand that this is something that uses only in the electrolyte iron, salt. In this case, they use potassium chloride and water, potable water, and there's nothing corrosive in this electrolyte, and it's the lowest cost electrolyte, which will last the lifetime of the battery. They have two platforms. The one is the energy warehouse, which is a battery in a container, and it's low cost, it's non-toxic, non-corrosive chemistry, no cooling required up to 50 degrees ambient, and that suits us in Africa. They are already in many military applications for the US Army and Navy. It's used in agriculture and industry and microgrids for remote communities. It has a low energy density, but it's not critical where you use it in rural applications or for large solar and wind farms. In Africa, we have lots of space. It's not made for mobile applications, of course. So where energy density is not critical, this is a very good solution. It currently comes with 50, 75, and 100 kilowatt, 500 kilowatt hours duration. The energy capacity is determined by the tank capacity, and that's what you can fit into a 12-meter container. However, there's for large applications, there's the energy center, which is a battery in a building, and they come in units, building blocks of 3 megawatt, 36 megawatt hour blocks, and you can scale this up as you like. I'm currently working on a design for a large battery in South Africa. It's combined solar and wind farm with a 50 megawatt battery, 600 megawatt hour duration. And that seems to be on track as we go ahead. Then the next one is hydrogen and fuel cell. Hydrogen is a big story at the moment. You can actually now buy a hydrogen-powered Tesla in the Netherlands. They call it the Hesla, and it has a range of over 1,000 kilometers. But there are other manufacturers working on hydrogen plus fuel cell for their vehicles, Toyota, Honda, Hyundai, etc. And it used to be quite expensive. It still is as a fuel, but there are lots of developments going on. Anglo American and Impala Platinum is promoting this because it's promoting platinum, and it is currently developing a huge market for that. They're also using it already for forklifts and developing heavy vehicles for underground mining using electric drive with hydrogen as fuel. So in South Africa, it is becoming a big story. There's also lots of hydrogen buses already running in London since 2010. Hyundai is selling hydrogen-powered vehicles. Toyota is now, I will get to that just now, fuel cell electric buses, more than 14 million kilometers done in China already, and it's used for light rail applications as well. And then there's the fight between fuel cell and battery for large trucks. Nikola Truck, they are putting their money on fuel cell, and Tesla on lithium-ion. But I believe for large trucks and trains and planes, for that matter, hydrogen drive will be the winner in the end. Sasol and Toyota is planning a massive green highway project for South Africa using hydrogen to power trucks between Gauteng and the Durban harbour. And this is now been released quite recently, and that will really put hydrogen on the map in terms of mobile applications in South Africa. Anglo is exploring the use of hydrogen in a liquid form. Hydrogen can be transported and stored in the form of ammonia, for example, and there are other liquids that can be used for this purpose. And now Anglo American is doing research to put a converter inside a car, so you can actually have a liquid hydrogen that can be distributed through the current fuel network and fuel stations, and it can be pumped into a car, and on board you will be able to convert that to hydrogen gas and power the fuel cell in the end. So this is not rocket science. It's really coming off the ground, and it won't be long before this will be a practical thing. The one project that I'm working with is for the batteries, actually to produce hydrogen for export in the form of ammonia to Europe. So also for large ships, this is pitched as the future, to get ships to go green, and hydrogen is probably the best fuel for that purpose in future. Liquid hydrogen, in fact. And for South Africa, there's a huge opportunity. We hear more and more that in South Africa we have certain areas where we have a good combination of wind and solar power, where we can produce lower cost green hydrogen than anywhere else in the world because of this combination of high solar energy and wind energy. I've actually heard, I was in a conference call just before this, and where the gentleman actually told us about what he's observed there, and he's now working on such a project for South Africa. But there's a huge opportunity in exporting hydrogen in South Africa specifically, because we can compete on price. I'm not going to look at the detail here, you can look at it afterwards, but it just shows the low carbon hydrogen supply chain, the vision for 2030. In thermal energy storage, we have what we know in this country already, molten salt. Crushed rock and sand is an excellent storage medium for heat, energy in the form of heat. And there's molten silicone, it's a new development in Australia. And then EnergyNest is a company that I've worked with, who uses a special concrete that can take the heat and store it for long duration storage. A molten salt is the salt is stored at 566 degrees C, but the problem is when this freezes, then we have big problems, and it's quite a risky business. It needs exceptional operational management to keep this going, and also it takes a long time to commission. It is more expensive than other forms of solar energy, but it does include storage. Now, it has helped us in South Africa to understand the value of storage and long duration storage, but I believe there are better storage mediums coming on the market. There is now a new project like this coming up, but it will be using the hyperbolic trough concept, but still molten salt as the storage medium. EnergyNest uses a special concrete, which they call heatcrete, which was developed in Germany. And this is an excellent medium, but they're not fully commercialized yet. And there are many applications. I have worked with them on certain, this specifically was ArcelorMittal in Saldanha, on recovering heat energy lost to the atmosphere, and then to reuse it as heat or as electricity. But sorry, I have throat infection. Let's take it. And the plant was closed before we could fully develop this concept. But there are many applications for this. They are now starting to replace the molten salt applications. They're doing the first project now in North Africa, and just the capex cost of this is up to 61%, depending on the storage size, and down to 35% lower than molten salt. And the OPEX cost is a mile of difference between it. It's just not as complex to manage and to maintain. Then there's a new kit on the block as well, 247 Solar, which uses sand as medium, and they use smaller solar farms with mirrors and a collector, which is only 35 meters high, and they are in the process of commercializing and building their first plant, but we're keeping tabs on this, and I am in contact with the manufacturers to follow this technology. And then there's the Energy Vault, mechanical gravity systems, which I'm not too excited about. It's a Swiss technology, but these bricks that they pick up and down here are 35 tons each, and they are picked up with cranes, with pulleys, and replaced, and as the energy needs to be stored and then released by dropping the brick. But I have many questions about this. I mean, what happens when we have a wind? And what about mechanical wear and tear? And what about maintaining up there in the clouds, maintaining all these mechanical systems? So I do have some problems or issues with this, but let's see where it goes. So that's the whole lot. What they say is the next generation smart grid without energy storage is like a computer without a hard drive, severely limited. And that's what we're seeing in South Africa and many other countries. And that is why there is now such a need and a requirement for adding utility scale and mini grid scale storage all over. But we need to keep it clean. Good, that's my story.
Thank you very much, Chris. Just going to try and change some things. We've unfortunately lost our key presenter or host because of load shedding. So I think we need to ensure that SAIEE is the first recipient of one of your test storage plants. Am I right, Chris? I think that would be great. I just want to try and change it over quickly. If everybody can just bear with me for 2 seconds.
My screen.
Yeah, I just want to take your screen off. So we need to go to the next part of of the session, which would be the questions and answers. Sorry, I am having a battle with this. Chris.
Good.
Sorry, I just quickly want to switch over here. As you can see, I'm not very used to with the go-to, so I apologize to everybody. Right, Chris, we thank you for that. This was indeed a very broad-based presentation. I think you've covered an amazing amount of technology and you've packed a huge amount of information in there. If we take cognizance of an important statement, the electricity business of tomorrow is being built on the business of today. So therefore, the role of this nascent disruptor, I think, is going to be huge. You have to agree. We have to ensure that we do this right. So I think that from my side, as an avid champion of all things storage in South Africa, I note that energy storage is not just a primary source of energy, but it's also a facility that can change the time from any low cost and hopefully clean primary energy sources is used. So it's often associated with renewable energies, fixing distribution, embedded storage generation on its own can have significant demand side management benefits, alternative energy integration potential for grid operators, and of course, great economic development potential exists for South Africa, something we're all looking for. So with that said, I think I want to go to one of the first questions for you, and I think it's an important one because maybe this is a nascent environment and it's new for everyone. And I think sometimes we sort of expect everyone has figured it all out. So you've done so much research. I'd like to ask you, how does one find the right size battery for a renewable energy mini-grid solution?
Yes, I find that many electrical engineers don't really know where to start with this. So I have worked now for some time to actually find a process whereby one can do this, because it is this energy or renewable energy ecosystem is quite complex when you have solar and or wind plus a battery plus maybe backup generators, and there isn't one combination of this that can actually work. There are many different combinations that can provide you the energy to run a specific energy profile. However, they come at different costs. So I have developed a methodology whereby I have a performance curve for a battery of a specific specification or configuration, and then I can develop several battery configurations and see how much PV energy is necessary, and then what percentage of backup energy you would need per annum, 2.5 or 5%, whatever is the lowest cost. But on this matrix, one can now calculate the cost for each combination of battery and solar and wind and backup generation, and in this way you can find the cost optimal. And what I have found doing this, and I've run this on flow batteries mostly, but also on lithium batteries, is that and this proves the point about long duration storage, is that one cannot compare sorry, battery prices based on the kilowatt power output, but rather on kilowatt hour capacity. And it's important to understand that you need to look at the performance of the battery and also the performance over its lifetime to actually find the best size at the best cost for any application. So it's important to also use a stochastic model. I had a meeting last night with an American vendor, and he says, well, you don't need to look at the energy profile, usage profile per hour over a year, or the solar energy per hour over a year, and it is just so wrong. You cannot work on averages or total values. You need to look at the hourly energy consumption profile of a specific application versus the hourly availability of solar and wind or wind energy every hour of the 8,760 in a year, so that you can have all the possible combinations between weather and energy consumption, and that will give you the ultimate result of the ideal battery size and the ideal PV size or wind capacity size. So without doing that, you will be missing the boat. And I think we can have a follow-up session just looking at how to size this. But that is a complex issue. You cannot do this on the back of a cigarette box if you're still smoking. But it's important that we understand this process of finding the optimal combination of these different components of the energy ecosystem.
I agree with you, Chris. Thank you. Yes, I think really that we could really develop a webinar with a deep dive into the sizing. It's obviously critical. I love the idea that you're using the hourly ratio for the year, because there are so many variables. If you go from the load profile of the client that you're trying to put the battery in, so it becomes critical to match it. And obviously optimizing is a key factor for the economic viability and the financial viability of the project. And also a person doesn't want to undershoot it. I mean, we've heard so many stories of, oh, my system doesn't work, but that's really just because the initial design didn't match what the load that it wanted to complete.
Absolutely.
I'd like to then stay on that tactic, but maybe just ask you, we said now, we have to design and optimize, for best, and obviously gives you the best option for pricing, because now you're doing a kilowatt hour scenario. The client knows he's now satisfied his need for security of supply. He's satisfied his need to reduce his costs. Maybe he wants to do a little bit of load clipping, arbitrage. He's now got the optimum solution. But now, if you had to look across the technologies, how do you feel the market currently sits according to pricing, if we had to compare technologies to price?
Yeah, well, depends on over what period you're talking. If you don't have a longer term, medium to long term view, then obviously at the moment, if you just look at kilowatt, lithium batteries are the cheapest, lowest cost. However, one cannot just do that. Once you look at the battery performance over a 10-year or a 20-year period, and the duration of the storage, if you add all of those factors, then the flow batteries actually come in at the lowest cost. Supercapacitors are still more expensive. I believe they have a very special application. They are already doing megawatt hour supercapacitor batteries, but it's still costly. For mobile applications, I believe they will become competitive, and even residential applications, they coming close to the Tesla wall battery, but with the difference is this thing lasts forever. You don't have to replace it, and your performance doesn't go down. So it's again a complex issue, because you need to keep in mind that on for example, lead acid and lithium batteries, you don't have the full capacity available. So when you compare price on terms of kilowatt hours, which is the better comparison, even just looking at capex, then lithium batteries, you need to reduce that kilowatt hours available to 80%, which is what you're allowed to utilize within your warranty, and so on. It's but lithium is, if you just look from the outside, is the cheapest battery, but it's not ideal for utility scale where you need longer duration and a long life. I mean, a PV farm has a life expectancy of 20 years or more. Lithium batteries just doesn't get it, especially if you use more than one cycle per day, and therefore I believe it's
Agreed, Chris. Are you still with us, Chris? Hello. Oh dear. Well, ladies and gentlemen, it seems like we've lost Chris there for a moment. Chris, I do know we just changed the time over to 7 o'clock, so I'm wondering if it's load shedding or but what I would then like to encourage everyone is to, are you back, Chris?
Yes, I'm here. Did you miss me?
Oh, great. Yes, I thought you had disappeared. I was just getting panic stricken because we still want to hear some more. Okay, so thank you for your for your inputs on the pricing. I do agree. It's about the optimization. It's about the right product. And I think that just flatlining benchmarking prices is not the way to do it. And that's specifically why I wanted to ask you that question, because each technology has its own merit in its own right, in its own placement, and there's no one off the shelf solution. So yes, I think we really do have to look at that design course or seminar of yours. Right. Looking through your presentation, Chris, I think that we obviously see your passion lies with the flow batteries. Can you tell me what you feel is a key design characteristic that would distinguish flow batteries for you? Why are you so passionate about the flow batteries? Chris, I think you're on mute. Chris, are you with us? Okay, well,
I lost
back?
you, but yeah.
Okay.
Somewhere
Did you manage?
there's a server with the power down, I suppose.
Yeah, where the power is out, I suppose. Did you hear my question, Chris?
No, just repeat that, please.
Okay, I said, looking through your presentation, we note that you are very passionate about the flow batteries. So from our perspective, and noticing that you're such a distinguished intellectual on batteries, what would you say is the key design characteristics that distinguishes flow batteries for you, and why you have a special spot for them?
Yeah, the most important design feature is the fact that your kilowatt hours, your energy capacity, and your power output, the rated power output, is not fixed, because your energy capacity, depends on the size of the tank, and the tank sits outside of the power producing component or the power cell. And this means that you can actually have a 4-hour battery or a 10-hour battery or a 20-hour battery, depending on the size of the tank. So you can actually make it according to, you can custom build it. Now for the smaller batteries up to 1 megawatt, for example, they are trying to get economies of scale, and therefore they have some fixed configurations. But once we get to utility size or mini grid size of 2 megawatts upwards, this is not a constraint anymore, because the energy or the battery in a building concept means that you have an external tank, and you can size that to whatever your need is.
Thank you, Chris. That was informative. I think it's given us some room to thought, and I think we would like to hear more. At this point, I still have 2 more questions for you, but I would like to just encourage the participants that we would welcome your questions. There is a email address for the Energy Storage Chapter on the SAIEE website. You can please send us the questions, and we'd love to answer them and hear more. And I'm sure Chris would love to respond to you, as well as we'd love some of these attendees to come and join the Energy Storage Chapter and to hear more about everything. Right, Chris, let's go back to the questions. Are you ready? We're drilling you. We're drilling your knowledge. Let me see. Supercapacitors, we saw, are designed for short bursts of power. We all have an understanding of that. Would you mind explaining to us how you feel a supercapacitor then can actually be classified or called, in effect, a battery then? And also interesting, how does it then relate to powering electric vehicles in the same ways as lithium batteries do?
Yeah, supercapacitors are a special animal, having a very long life. I mean, there's no limitation on cycles. And the key thing is that you actually store electricity as an electric charge. So you don't convert it to a chemical energy first and then revert it back to electricity. So that makes it special, and that gives you a round-trip efficiency of 99% on the DC side. You have a bit of loss through your inverters, etc. Now, the supercapacitors are extremely useful for electric vehicle application because you can charge it so quickly. So once they can get the energy density sufficient for longer range, which is quite close now, it will become much more popular. The cost is coming down now, even before they get the economies of scale that we have with lithium batteries, because of the new technology of construction using a prismatic construction instead of rolled sheets. Also, what is important, I think, especially in industrial applications, is that you could have a battery. It has a much higher energy density than flow batteries, for example, which you cannot easily fit into a dense industrial site. However, with the supercapacitor battery, you can do that, and you can have automatic power factor correction. Supercapacitors has been used for some time now for power factor correction, but when you use it as a battery, you still have that ability to do power factor correction, and there are many factories with older equipment that's running at 60 or 70 or 80% power factor, whereas with the supercapacitor battery, if they use that for other purposes, they will also be able to increase their power factor significantly. So that's one of the key issues or factors with supercapacitors. But in the electric vehicle market, there are two things: its ability to regenerate power at a much higher rate than lithium batteries, and secondly, you can charge it quicker than you can fill your tank with petrol.
Wow, that would be the new world that we're moving into. Am I right?
Yeah.
Chris, we have a lot of end uses for storage. I mean, we've got the grid, standalone, co-located, large scale, small scale, microgrids and that. But I think one of the sectors that has got a huge challenge at this point in time would be our heavy industrial applications, our mines, the factories, especially those with furnaces and the like. These are very challenged industries. I mean, if you see with the challenges we've just had with this webinar now, where we've lost one presenter, the other one trying to come on, it's having an impact. And I know personally that many of those sectors are looking to implementing storage. Which path would you encourage an industry in an industrial application to follow? What would be your choice, if you can share with us, just to open our minds and start thinking of how we start applying storage into the market?
Yeah, well, I don't want to use this platform for advertising, but I am working with several mines on planning battery storage, and especially where you have industries where you have to work 24/7. A mine cannot be profitable if you don't run 24/7, and then obviously you cannot just go off the grid and be dependent on wind and solar alone. And that's where a flow battery with a large energy capacity can actually come to the rescue. And also because of the kind of cycling that they have. But we are working with several mines. We're talking about a 84 megawatt battery, and it can push out that 84 megawatt for 12 hours on end for a specific mine. And there are several others. There are even mines with something like 160 megawatt load 24/7, which wants to go off grid. So that I would think is the way to go, is really look at long duration. Forget about the technology. The technology they will find, they're looking for long duration. And this is also the trend now in the US, and especially California. Sorry. The mining and heavy industries really need to look at long duration and long life. I mean, you cannot, a mine cannot work with something that they need to replace every 10 or 15 years, and that is has a degrading performance over that lifetime, or need to be augmented. So I think that is more and more industries are coming to this view that lithium is not the answer for that. They need long duration, they need long life, they need low cost of storage over the lifetime of the plant. And once you start making those calculations, then the answer is not that difficult. There are, of course, different flow battery technologies, and I think the one with the lowest cost in work, also one that is scalable enough. I believe this iron flow battery is the only one that has a real scalable building block of all the flow battery technologies at this point in time.
Wow, thank you, Chris. I think that was great. We've got some massive insights into it. I think that we did touch on pricing and that, but if we look at where the energy price is now, we can definitely prove with all your technologies that storage can hit grid parity. It's an option that we need to look at. If I can close on saying that, and then I'd just like you to give your closing comments. For me, energy storage can be applied to optimizing energy procurement costs. It's going to protect the economy. It's preserving overloaded distribution infrastructure. It unlocks development. It definitely supporting of densification. It really does help to make the business case for the renewable energy systems. It optimizes that investment. And then it really does provide the basic energy services and ancillary services that we see. Is there anything else that you would like to add as your closing statement, please, Chris?
Yeah, just maybe one point that I did not emphasize is also the issue of frequency regulation. I have just worked through a simulation for a large battery to be used for frequency regulation, and that is quite an important role for large batteries at this point in time. In Europe, they are switching from gas peaking plants to batteries in a big way, and the first one in South Africa is now being developed for that purpose. But
Fantastic.
maybe just in conclusion, I think with batteries, we should look deeper into what you get and what the lifetime is, and also look at whether it's clean technology that will last for a long time.
Amen to that. We definitely support that. We all know that South Africa's got to make the move to the just energy transition, and definitely storage is going to be one of the foundation points to help us enable that transition. Chris, thank you for a very informative session. I think that you are going to be bombarded with questions, and I think that we do need to take a couple of your elements and have a deeper dive, unpack on them, especially on the optimizing of the sizing. For SAIEE, I would like to thank the platform and the hosts for making this opportunity. To all the attendees, and Chris, you must know they all stayed on. I haven't seen any drop off, so you've done exceptionally well. They obviously want to stay and hear more. I encourage everybody to engage with us, to join the energy storage chapter, to come be contributors, if either to contribute or to come and learn. You're all very welcome. This is definitely the technology that's going to be leading South Africa, and I think is already moving into pole position. So without that, I would like to say thank you to everybody for being here, and may everybody have a good evening. Be spared from the load shedding, and we hope to hear more from you. Thank you, everybody.
Thank you. Bye-bye.
Bye. Bye.